Why is the unit circle key for IIR filter stability? Have you ever wondered why the unit circle is so important in the world of infinite impulse response filters? Let's break it down in a way that makes sense. The unit circle is a fundamental concept in electrical engineering, especially when we talk about digital signal processing. It helps us determine whether an IIR filter is stable or not. First, let's understand what an IIR filter is. An infinite impulse response filter is defined by a transfer function in the z-domain. This transfer function is essentially a ratio of two polynomials. The roots of the denominator polynomial are known as poles. These poles are critical because they dictate how the filter behaves over time. Now, what do we mean by stability? In simple terms, a filter is stable if its output remains bounded when given a bounded input. This is known as bounded input, bounded output stability. For an IIR filter, this means that the impulse response should decay to zero as time goes on. If it does not, the filter can produce outputs that grow indefinitely, which is not what we want. Here comes the unit circle into play. The unit circle is defined in the complex plane as the set of points where the magnitude is equal to 1. This circle represents all possible frequencies in the discrete time Fourier transform. For an IIR filter to be stable, all its poles must lie strictly inside the unit circle. When the poles are located within this circle, the impulse response associated with these poles will decay exponentially over time. This means the filter will behave predictably and remains stable. On the other hand, if any pole is located on or outside the unit circle, the filter becomes unstable. In this case, the impulse response will either not decay or will grow without bound, leading to unpredictable behavior. It's interesting to note that this concept isn't just limited to digital filters. In analog filter design, stability is ensured by keeping poles in the left half of the S-plane. When converting these analog filters to digital ones, the left half-plane translates to positions inside the unit circle in the Z-plane, maintaining stability. Moreover, the existence of the discrete time Fourier transform of the filter relies on the region of convergence of the Z-transform, including the unit circle. If the poles are outside this circle, the frequency response becomes undefined or infinite at certain frequencies, making the filter impractical for real-world applications. In practice, designers pay close attention to the location of poles during IIR filter design. The unit circle criterion allows for easy graphical checks using pole zero plots. Ensuring that all poles are inside the unit circle is essential for the filter to produce a bounded and decaying impulse response. This is vital in control systems and signal processing applications where reliable and stable behavior is a must. So, the unit circle serves as a boundary that separates stable from unstable pole locations for IIR filters. Keeping poles inside this circle is necessary for a well-defined frequency response, which is fundamental for effective digital signal processing and control system implementations.